we start with module 4 physical layer, and in today's module 4 physical layer module, we are going to talk about, let me get my pen first. Okay, so we will talk about the purpose of the physical layer. We will describe it, like why do we need a physical layer and what are its characteristics, what are we looking for in physical layer, what are the problem basically that we are trying to solve, and then we will move on to the importance and characteristics of copper cabling, UTP cabling, fiber optic cabling, and wireless media. So basically, we will cover everything that there is at CCNA level in the physical media. Now, before I jump into these topics, I just want to talk about, well, let's get into purpose of the physical layer and start talking about it, okay? So for a while, just forget about this text. Let me get it here. Okay. All right, Asif, you can't hear me, but other people can hear me. So yeah, just get out and come back and we'll see if that fixes it. All right, so we talked about the OSI reference model where we have 7 layers, right? So we talked about 1, 2, 3, 4, 5, 6, and 7 layers. And now we are getting into the details of each layer. So we will have a module at each layer explaining what this layer responsibilities are, what problem this layer is actually solving. We're starting from the bottom. So this is the bottom to top approach. Some people also teach it from top to bottom. So they start with layer 7, explaining what a layer 7 is, and then move down at layer 6, 5, 4, 3, 2, 1, reaching the physical layer. But most of the books and Netacad as well starts explaining it from bottom. So we go through the sequence of 1, 2, 3, 4, 5, 6, where we have first one is the physical layer, then we have a data link layer, and then we have the network layer and transport layer. Number 5 is session, and 6 is the presentation, and 7 is the application layer. All right. I also want to repeat that this is the OSI reference model. Okay. So reference model, remember reference model. Reference model means it's a template. It's a reference. Whenever we talked about the network stack, how multiple devices can communicate through a network, there is a suite of protocol that is needed because each protocol is solving a specific function, or it is solving a specific problem with a specific function, right? So each protocol has its own responsibility of doing its job. But the whole communication between multiple computers is not possible. It is not a one function problem. It's not a problem. It's not a small problem to be solved with a single function. It needs multiple functions, or in other words, it needs multiple protocols and multiple solutions all working together so that one computer can communicate through a network to another computer. Okay, it's a complex problem. And that's why we divided these problems into 7 different smaller problems, because it's a huge problem. So the smartest thing to do to solve a huge complex problem is to divide it into multiple smaller chunks and then try to solve each small problem individually in its isolation. And that's what we are doing here. So the OSI reference model has divided it into 7 distinct problems or functions, and each layer, these are called 7 layers of OSI, and each layer must solve a specific form of a problem. Layer 1 is called a physical layer, and physical layer is responsible of providing a functionality or solving a problem of the physical connectivity between 2 computers. Okay, so we have 2 computers, we want them to communicate together. What are the physical requirements for 2 computers to communicate together? We just focus on that. Okay, and that's what this module is about. So you have 2 computers. How do we make them communicate? Well, obviously, the first thing you need is a physical connection between these 2 computers. So let's just talk about that physical connectivity. So we can connect them with a cable directly. without needing any switch or a router or anything at all. It would still be called a network. Okay, so network is just two computers communicating, and if we just could connect them using a simple cable, somehow that would be still a network. But what would be the characteristics of this cable? How long it could be? Okay, would it be a copper cable? Would it be a fiber? What if we just connect it wirelessly? How can we do that? Like, there are so many things that we can do at a physical layer, right? And whichever cable or whichever method, physical method, and these are, by the way, called the medias. So this is a type of a media, like this is collectively called media. What type of media or a medium you're using to connect these computers together? It could be a copper cable, it could be a fiber cable, it could be a wireless connectivity. But whichever media you select to connect these two computers together, there's another question, like what kind of signals would pass through these cables? Would it be electrical signal? Would it be light pulse? Would it be electromagnetic waves? There could be a bunch of things. And then there is encoding problem, which we are going to get into it, like what is encoding? Okay. Other than that, we also have a problem of like, how would this physical cable look like in case if it's a copper cable? What are the voltage levels of the electrical signals that we are sending? How would they be defined? And then lastly, what is this connectivity? What standard we should use for the connectors that we are using that is going to actually physically connect to the computer? For the computer, there has to be some sort of a port where you can plug in the cable, right? That has to be very specific and standardized connector on the cable as well, and on inside the computer as well. There has to be a port where you can plug in that cable, right? We have to specify that as well. And inside computers, we have a thing called NIC, network interface cards. So in the computer, you must have a well-defined network interface card, which is inside the computer or laptop, which will provide you with that specific port where you can plug in the cable. So if you're using a fiber cable, then your computer must have a network interface card already installed on your computer, which has the fiber connectivity module, the hardware plug, where you can plug in that fiber cable, whatever the connector type of that fiber cable is. If you're using a copper cable, then your computer must have a network interface card which has the copper cable connectivity plug already installed in, so that you can put in a plug in that network interface card. If you are choosing a wireless connectivity, then you must have a wireless network interface card which must have a wireless antenna that works with Wi-Fi, let's say, so that it can transmit those Wi-Fi signals, those electromagnetic signals, right? So all these things that we're talking about here, they're all related to the physical layer, layer one. Everything that we just talked about, whether we talked about signals, whether we talked about cables, fiber optics, wireless medium, encoding, signaling, the network interface card plugs, connectors, wires, everything is defined by layer one. So layer one, physical media, is only talking about physical things that you must need in order for two computers to communicate together. Okay. So now keep that in mind, and now we can move on with our module and see and describe all these things. Okay. So the physical connection, or the purpose of the physical layer. So before any network communication can occur, a physical connection to a local network must be established. We already talked about that. So you need some sort of physical connectivity before we can communicate. This connection could be wired or wireless, depending on the setup of the network. It depends on whatever options you have, what type of network interface card you have on the computers or on the mobile phones. Do you have access point, a wireless access point, or do you have a copper switch or a fiber switch? Ali Raza, where I find all the recordings in any group on WhatsApp. Ali Raza, if you are part of the group, we always share our recordings in the group. So you would be finding it in the group. If you're not in the group on the WebEx, then send me an email or check your email inbox, spam folder. I sent the link to join the WebEx group in your email. But if you can't find it, just send me an email and I'll give you the link again. Okay. All right. So all the classes are being shared after we finish the session. So I don't know exactly why are you asking in the middle of the class where the recordings are, because you could have asked it anytime. Anyway, you'll get them. Somebody posted it as well. Okay. But KB and Route, just don't post them in these chats, because he would need the group. He needs to join the group, because we cannot share it always in this chat, because this is a chat specific for this session. When we get out of this session, it gets removed. All right, so we'll continue. So this generally applies whether you are considering a corporate office or home. So again, same thing. Depending on the situation and the equipment available, you would pick or choose that whether your network would be wired or wireless, depending on what devices you have and what cables are available and so on. A network interface card that we just talked about, it connects a device to the network. Okay, so remember, if you have a computer or a laptop or a mobile phone, it must have a network interface card, okay, which comes pre-installed on most of the devices, but you can also buy a separate network interface card. If you have a modular PC, you can connect it. There are slots where you can add extra network interfaces card in servers usually, but laptops usually come pre-installed with these days. But there's a possibility that your network interface card that comes pre-installed in your laptop, let's say, it's not working anymore. Something happened, its chip is not working, or it was toasted or whatever. So it's possible that if you have a USB port, which all laptops would have, you can just buy a USB-based network interface card and plug in here. So for example, most of the people who have Mac, and I also have a Surface, they don't have the network interface cards pre-installed, where I would have an RJ45 plug where I can connect the cable. They do come with the wireless network interface card. So inside each laptop or inside your mobile phone, so you have this antenna inside your laptop. You cannot see it, but it's fixed inside. So that antenna is basically your wireless network interface card. Similarly, inside your phones, I'm just creating this antenna with the phone, but with phone, your antenna is basically inside your phone casing. You cannot see it. It is packaged inside, but there is an antenna in your mobile phone for the Wi-Fi, and that is the wireless network interface card in your phone and laptops. But just in case, if you need to put in a cable like Ethernet cable into the laptop to connect it to the network, you would have to buy a USB converter, which you can connect, and then it would have a port here where you can connect the copper cable with RJ45 connectivity, right? So that's the solution that we have. If you had a server, then you would have to buy a network interface card that you can plug into the server, and you can have multiple network interface cards in your devices as well. It's not limited to one, but you need at least one network interface card in order to connect to any type of network. Okay, so I hope that is clear. So network interface card is an important component of your devices. So you cannot connect to a network without a network interface card. Say from now on, we will just call it NIC or NIC. Okay, so some devices may have just one NIC, while others may have multiple NICs, wired or wireless, for example. That's totally possible that one device have multiple network interfaces card. Usually laptops would have it. You can plug it to the cable with RJ45, and it can also connect to the Wi-Fi. So Wi-Fi is a separate connectivity. It requires a separate network interface card. cable requires a separate network interface card, okay? Not all physical connections offer the same level of performance. Obviously, based on what you choose or what type of your network is, different network interface cards for different medium have different performances. So a wireless connectivity is not the same as copper connectivity, which is not the same as fiber connectivity. They all have different bandwidths, limitation, characteristics, which we will talk about, and we choose which type of media we connect to based on those characteristics and limitations, okay? So this is how the physical media, we talked about it previously as well. So your data, this is what comes from the application layer. So at layer 7, when you're working on an application like on your browser, or when you are sending an email, you create data or generate data. User generates data. You typed in an email, hello, how are you, where are you, I have some files that I'm sending you, and so on. That's the user level data that you are generating, and you give it to some sort of an application that will try to send it. So you give that to the application layer, and application layer sends it to the, this user data is sent to the the transport layer, where the TCP adds its own header, and these are the names, these are the PDU names, protocol data units. Remember, we talked about it last time. These are the protocol data unit names. So at the application layer, the protocol data unit is called user data. When it is sent down to the bottom layer, which is the transport layer, where TCP or UDP would add its own header. So this is an example. It just says TCP. Instead of TCP, it could also have been UDP. We could use multiple protocols in the same layer. There are multiple protocols that we can choose from. In this case, it has been chosen to use TCP. So TCP would add its own header. And this process is called encapsulation. When data is sent from one layer to another layer, the PDU changes because extra bits or header information is added by the next layer. This process of adding the next header information is called encapsulation. So through encapsulation, a PDU changes. So a PDU going through the encapsulation changes from user data to a TCP segment, and then it encapsulates it again, adding the IP header information, and it becomes an IP packet. And then it's given to the Ethernet layer, which is the bottom layer. It becomes an Ethernet frame. And this Ethernet frame is the actual full frame, which includes everything. It has everything now. That is actually going to be converted into bits and sent through the physical medium. So this is where your web server has the network interface card, which is plugged into the copper cable. And now this whole process that we were seeing, this happens inside the server software. This is a piece of code that's doing, you opened up an email application, you typed in something, and it went through this process of encapsulation, adding more information to your user data. User data became TCP segment, then it became an IP packet, then it became a frame, and eventually when it became a frame, it will be converted by layer 1 into bits and signals eventually, and then sent out using this physical cable. And that's how it will go on and reach here. And then the reverse process would start by this NIC inside this computer, which will convert it back to data from bits to meaningful information frame. And then it would start removing this Ethernet frame after reading it and processing it. And this removal of this process is the reverse process, called de-encapsulation. So de-encapsulation happens on the receiving end, and then it will keep reading and processing information and removing the headers. Eventually, it will get to the data and actually receives the email and reads it on the screen, the other person. Okay, this is how things are working in network. So I hope now you understand like where the physical layer lies in this OSI reference model, and what is the purpose of the physical layer. The purpose of the physical layer is to actually physically connect different devices together and transmit data across those physical media. Okay, so let's talk about the characteristics of the physical medium. First of all, these are the standards. So we talked about different organizations that looks for these standards so that they make sure that all the computers, vendors, and different organizations who are creating computers and mobile devices for networking, they follow a same standard so that everyone can communicate together. All other higher level information, this is governed by IETF. Okay, this is governed by IETF. They are responsible of looking at the standards that everyone is following when they are creating new protocols or adding modification, optimization, performance to optimize its performance, and so on and so on. For the physical layer, in some part of the data link layer, you see this? So some of the organizations are responsible only for maintaining the standards of physical layer and some part of data link layer. So this is some part of data link layer. We're talking about it. The reason for this is that whenever you see these layers, we're talking about OSI layers, right? But as we talked about previously, the actual implementation that in your computer is the TCP/IP stack, not the OSI layer. So OSI layers are layers, 7 layers, which is what we talked about when we are discussing and explaining and writing protocols. But the actual protocols that get installed is TCP/IP, and TCP/IP considers the data link layer and physical layer as a single layer. And the reason for doing that is because in actual, you cannot separate data link layer from the physical layer. There is tight coupling, because if you change something on the physical standard, the data link layer things needs to be changed as well. You cannot just change something in the physical layer and assume that nothing in the data link layer will change. Although the idea of creating layer was that if you change something in application layer, it would not affect anything in other layers. That is the idea, but that idea doesn't always work. Largely it works, but in some cases it doesn't work. So this is one of the cases that the physical layer, whenever you make some changes in a physical layer, you have to make some changes in data link layer as well. And we will talk about those things later, okay? But for now, the important part is the looking at the difference that for all these layers, we have IETF that are making sure that the standards are followed. But look at the physical layer. There's so many different organizations that are looking at the physical layer to make sure that the physical layer are not are following standards. You have ISO, EIA, TIA, ITU-T, and CCNA IEEE. Why so many organizations for one layer? That tells you that the physical layer is very complicated in itself. It needs so many different things to be looked at that it needs different organization for all those things. So, for example, where is my pen? The EIA, TIA looks at the connector standards. What type of connectors can we or should we use? That's a whole different world. That's a whole different problem that needs to be solved. Okay, IEEE looks at the, let's say, signaling and the electrical components of this physical medium, and so on. Okay, so physical layer standards address 3 functional areas. It addresses the physical components, which is what we are so far talking about. The physical components are the hardware devices, like NIC itself, the media, meaning cable, fiber optic, and wireless medium, and other connectors that transmit the signals that represent the bits. Okay, so hardware components like NIC, interfaces, connectors, cable materials, cable designs, all specified in standard associated with physical layer. So that is the big part of physical layer standards. which layer 1 or physical layer has to address and define all these things. That's one part of it. Now, there are some things that are not physically visible that you cannot touch, which are also part of the physical layer. That is encoding and signaling. So you might understand the signaling part easier. So if I just explain it, like what is signaling? Signaling is the selection of what kind of signal would actually physically travel on the cable. So like electrical signal, that is signaling. It could be electromagnetic waves in case of wireless, or it could be just light pulses if it's fiber optic. So that is signaling. And that's, no, it's not that, Wahab. We're going to talk about it. That's more like encoding. Okay, so I'm leaving the encoding for the last. So at the signaling, you select what type of signal you would be sending. But encoding is more interesting. Let's talk about the encoding first. Encoding converts the stream of bits into a format recognized by the next device in the network. Okay, encoding means, so whenever we have a frame that we saw in the previous slide, so when we get a frame and it's ready to be transmitted on the physical connections that you have, before you transmit that frame, you have to convert it into bits. And those bits will then be sent as a signal on the physical layer, right? But before you send those bits, there's another process that we call encoding, in which you convert those bits to some sort of meaningful bits, which would have more properties that a normal bit wouldn't have. Let me explain that. What do I mean by that? For example, you typed hello, right? And then that application got, it went through all the encryption process, the TCP header got added, and then the IP packet, and then the frame, and this is the actual thing that created. You just convert this into bits, and it becomes 0, 1, 1, 0. Just an example, obviously, if you convert this into bits, it would be a huge string of zeros and ones, right? But for sake of example, let's say the whole frame that we need to send is 0, 1, 1, 0 in bits. That's how we can represent this whole data in bits. And we want to transmit it. So the problem with this is that whenever if we transmit it like that, it is fine. It looks fine at this point, but it doesn't have any characteristics. If you keep doing that, you would understand that every time you are just sending some sort of random bits, right? What we like to do in physical signaling is that we need to do some encoding to add some more characteristics to this. Why do we need more characteristics to be added to this? For example, you create some sort of user data and so on and so on. And instead of, when you convert it to bit, instead of 0, 1, 1, 0, it turns into 0, 0, 0. That's totally possible. Or it turns into 1, 1, 1, which is totally possible. Now, if you start transmitting 0, 0, 0s or 1, 1, 1, 1, it starts causing troubles in the transmission on the other end because you lose synchronization, because your bits are not changing at all. If there is no change, that means you're not sending any information, and the other end actually has problems in receiving this sort of sequence of bits which are always same. It loses the timing. It cannot see where the bit starts and where it ends, and it starts drifting. So we need some sort of mechanism in the bits, and that's why we have different encoding schemes, methods like Manchester or 4B/5B, 8B/10B, which means that before sending this data, convert it or encode it. This is what we call encoding. Encode it into some other sort of mechanism. For example, 4B, 5B mechanism, if that is the encoding mechanism we use, that says that every time you have to send 4 bits, convert it to 5 bits. And there's a pattern that is already defined that if you get a 0, 1, 1, 0, convert it into 0, 1, 1, 1, 0. So now, and send these 5 bits instead of 4. What purpose does that serve? Well, it has a lot of characteristics. For one, that it doesn't allow sequence of zeros and sequence of ones, which causes problems. So if you have to send sequence of ones or sequence of zero, it will get first encoded into 4B/5B, and it has a pattern of, let's say, 0, 1, 1, 1, 1. Convert it to this number first. So this was 4 bits, now it's 5 bits, and then transmit this. And the other side, obviously, the receiving side would know that if it receives 5 bits of this pattern, this actually means 1, 1, 1, and it will convert it or decode it back to this, and it will receive this information eventually. But when you're physically transmitting it, you're transmitting this, not this. This is how you avoid same sequence of zeros or long sequence of zeros and long sequence of ones, which causes timing and synchronization issues between devices when they are communicating, right? So that's the purpose of encoding, and we have different types of encoding. There's 8B/10B encoding as well. Every time you have to send 8 bits, convert it first into 10 bits. And today in modern networks, what we use is called 64B, 66B, I guess. Yes, that's what we use in modern. So for every 64 bits, we convert it into 66 bits. So for every 64 bits you're sending, 2 extra bits are added, which gives it the extra characteristics, which helps us in synchronizations of the clocks between two devices. It avoids the long sequence of zeros and ones as well, and other properties which we don't want to get into at CCNA. Okay, but I hope this clears up what the encoding is, and this is also part of the physical layer standard, which has to define which type of encoding scheme is needed. Then the signaling, once you have converted or encoded the 4-bit or 5-bit, whichever you are using, or the modern one, which is converting, first you convert the 64-bit. So you had a frame and you encoded in using 64B/66B method. Now you got the 66 bits, and now you have to transmit these 66 bits using signaling, where you defined what a 1 or 0 means in physical cable, because essentially you are sending bits, right? Zeros and ones. How do you send zeros and ones now? Well, depending on which method you want to use. For example, in digital signals, you can just send 0 with a lower voltage. This could be like -5 volt, and 1 could be just +5 volt if you're using digital signals, depending on the cable. If your cable supports sending digital signals, you can just send -5 volt for a 0. Every time you want to send a 0, just send a -5 volt on the cable. If you want to send a 1, just send a +5 volt on the cable. Very simple. If you're using the analog signals, then you can use amplitude modulation, frequency modulation, phase modulation, different things that you don't need to really understand. You just need to know that zeros and ones can be sent using different methods. So in amplitude modulation, you can see that if you have a lower amplitude of a signal, that would mean it's a 0. If it has a longer amplitude, see here, then it would mean 1. So lower amplitudes 0, higher amplitude 1s, and so on. This is how you can send it. Or in frequency modulation, you can change the frequency of a signal every time you want to send a 0, so it has a lower frequency, less repetition of a signal. Every time you want to send a 1, higher frequency. Lower frequency 0, higher frequency 1, higher frequency 1. So you keep sending bits this way. Or with the phase modulation, you change the phase of the signal. Whenever you want to send 1, just invert the signal. Okay, so there are different methods. So this is for a copper cable. If you have a fiber optic cable, you can just send zeros and ones using light pulses. So switch on the light pulse. So you're sending a light pulse here, you switch on the light, and then it's dimming afterwards. So this could mean 1. So when you switched on a light, it's 1. If you're not switching on a light in a specific amount of time, it would mean 0. If you want to send 1 again, send the pulse again, and so on. So it depends on how quickly you can turn on and off the light in fiber optic, and that's how you can send ones and zeros. So that's the signaling part. So you first encoded using 4B, 5B, or 64B, 66B, convert it into a different encoding scheme, which adds more characteristics to the bits, then convert those bits into one of these methods, depending on which media you're using. You can send these zeros and ones using digital signal, amplitude modulation, frequency modulation, or just as a light pulses if you are using fiber optic. This is the signaling part, and this is not an easy thing to do. That's why there's a separate organization which looks into the standard. If you have to send 1 gigabit of data in 1 second, if you have to send 1 gigabit of data in 1 second, that means you have to switch on and off a light pulse in a fiber optic cable like 10 power 9 times. Like you have to switch on and off the LED or lasers inside your network interface card, which is actually sending these bits using light pulses. You have to have the ability in your electronic system to switch it on and off 10 power 9 times in 1 second. That means you have to do it within milliseconds or maybe nanoseconds. I don't know exactly. I haven't done the calculation, but just to give you an idea how hard it is to do this. We are just explaining it very simply, but this is actually a very hard problem for the engineers to do so. So that's why it has a completely different organization looking at the standards of how do we achieve this with this electronic component, doing it so quickly so that we can send 1 gigabit of data in 1 second. Okay, which brings us to the topic of a bandwidth, because that's actually defining a bandwidth. How much data you can carry within 1 second, that's bandwidth. So bandwidth is the capacity at which a medium can carry data. How much data it can carry? Well, we have to define a time frame in how much time. Usually that is a second. So amount of data that can flow from one place to another in a given amount of time. For example, how many bits can be transmitted in a second? That defines bandwidth. How many bits? So whatever signaling that you selected, whether it is this one or this one or this one or this one, whatever encoding scheme you selected, 8B, 10B, 64B, 66B, 4B, 5B, Manchester, and there are a bunch of others, you select these encoding, these signaling, and that defines how many bits can be transmitted in 1 second when you select these components, because all these components have these characteristics. It affects the bandwidth of your connectivity. So physical medium properties like current technologies and the laws of physics play a role in determining available bandwidth. Okay, and the bandwidth, the unit of bandwidth is bits per second. When we had a slower connection, we said bits per second. Then we got better connectivity. We improved these signaling and encoding methods. Then we got into kilobits per second and megabits, gigabits, and terabits, which is just basically adding 10 power 3 at each step. That's how we define bandwidth. How much data can be carried in 1 second in this specific media. That's the bandwidth. Now, there are some other terminologies related to the bandwidth. For example, latency. Yeah, your provider says 100 Mbps, but down is 10 MB. Well, that's a different trick. Actually, there are a lot of things are going. It's like a difference between a capital B and a small b, right? That's the actual problem. So when they are selling, because that's a marketing trick, when they are selling you a connection, they are using 100 Mbps with a small b, so that's 100 megabits. But when you're downloading a file, your browser is showing you the speeds in bytes. So that means you have to divide 100 by 8 because there are 8 bits in a byte. So actually, the connection that you have got is 100 divided by 8. Okay, so which is closer to 10 megabytes. That's why you see that. All right. There are these terminologies that are related to bandwidth when we are talking about bandwidth. First one is latency, which is the amount of time, including delays, for data to travel from one given point to another. So you have this computer, there could be multiple devices, but let's say they are connected with a cable. So this cable could be 100 kilometers far away. It's totally possible with fiber optic, by the way. I mean, nobody would do it this way, but it's possible. So if they are 100 kilometers away and you send a signal, so you have a fiber optic and you can send a signal from here, for you, it looks like it will instantly reach there because the fiber optic cable is sending information through pulses of light, and pulse of light as the speed of light, right? Which is what? I totally forgot. Like, what is the speed of light? It's roughly 3 into 10 power something. I forgot about that. But whatever the speed of light is, if somebody knows what is the speed of light, can you put it in the chat? That would be interesting. How did I even forget about it? But anyway, so the idea is, so yes, you can. So the idea is that the light has to take some time to travel from here all the way for 100 kilometers, right? It would take some time. Let's say it's taking 10 milliseconds. So this time it takes from signal when you generate a pulse here, and it takes 10 milliseconds to appear over here, that is called latency in simple words, okay? That is latency. And this latency, there's a physical, it's a physical thing, right? There has to be a latency. So now it was a direct cable. Now imagine it was not a direct cable. There were switches and routers in the way. Every time there's a device in the way, the device has to receive your signal, process it, make some decision, and then forward it to other device, and so on and so on. So if there are more devices, this 10 millisecond latency will increase depending on how many devices there are and how are they processing. So it could be actually 30 milliseconds in that case. Again, 3 into 10 power 8 meter per second. Yeah. So the speed of light is fixed. It cannot go faster than that, right? So that means no matter what the distance is, there will always be a delay when you send a message, and there would be a delay when the other side receives that message. That is called latency. And latency increases between two devices depending on so many other factors as well: the congestions, bandwidth, the processing, and how many devices in the middle you have, right? Actually, you can see the latency if we open up a terminal. So let's say I do a ping 8.8.8. So this shows me a round trip time. Here it is, a round trip time in milliseconds. A round trip time, let's say this one, it says 54, one of them was a 54 millisecond, right? Round trip time. That means my signal, when I sent a packet, let me get it here. So when I sent a packet from my computer to Google server, it went there, and then the Google sent me a reply back. That is called a round trip time, which was 54 millisecond. What would be the latency between my computer and the Google server? Well, it is divided by 2. When you divide the round trip time by 2, that becomes your latency, because latency is the single path it takes, not the coming back. So I generated a packet and it was received by Google server. That is latency. Okay. So this would be 54 divided by 2. Sorry. Okay. Where we were, 54 divided by 2, which is 27. Okay. So your latency would be 27. So I hope latency is cleared. Then you have throughput, which is the measure of the transfer of bits across the media over a given period of time. So this latency or round trip time, this is for single bit. how much time a single bit is taking when it's generated from here and when it reaches here, there will be always some sort of latency. But then there is a measure of a transfer of bits across the media over a given period of time. But within a one period of time, how many bits you can quickly generate and send within 1 second? That is called throughput, which is usually very high, that these computers can generate a lot of data in 1 second. Okay, but there is always a lot of overhead on the throughput, because when you are sending just a hello, you're not just sending a hello, you're sending the whole frame, which includes TCP IP header, the network IP header, and the frame header. And there are other bunch of information overhead. We call these overhead because you actually, the interesting data is this hello, but we have to add all these data to add more characteristics to the information so it can be reliably sent over, right? But eventually, when you receive, you only receive this. So for example, if this was 5 bytes, you actually had to send 8 bytes. So this 8 byte is actual throughput that you are sending through the through your connection. But the good put is only 5 bytes, because this is the actual information we needed to send. So good put is actually the throughput minus traffic overhead that you had to send, which was here. So our whole throughput was 8 bytes, 3 bytes for, let's say, let's take another example, not this example because it's getting complicated. So for example, you buy something from a shop and it comes in a box, right? So let me create a box here. So it comes in a box. So let's say this was something like you bought books and they got parceled at your home and they charge you through the weight of the package, right? So the total package, the total weight of this package was, let's say, 5 kg. But when you open it up and you take out the books and you weigh them down, the books total weight of the books was, let's say, 3 kg. The 2 kg extra was the weight of the box and the bubble wraps and other things to keep the books secure in one place, right? So the 2 kgs was extra. You had to pay for the 5 kg. So this 3 kg, the actual books that you needed, is your good put. This is what you actually needed. But you couldn't have got them without this traffic overhead, without the box and the bubble wrap. Okay, so that's why you had to add plus 2 kg, which was the overhead. And now on total, you had 5 kg that you actually sent. That was your throughput. So your throughput was 5, but your good put was 3. This is what is happening in the bandwidth as well. Your throughput is, let's say, 1 MB connection, but the actual data that you get is not 1 MB when you're downloading it in 1 second, because there's always overhead, retransmission, and other things that you don't need. You just need that one file to be downloaded. That file is not 1 MB, and still it's taking more than 1 second to be downloaded. Okay. So I hope these terminologies were clear. Now we can move on to describe what is the copper cabling, the actual physical cable. So copper cable is the most common type of cabling used in networking. And the reason for that is why it's copper cabling. So how about jitter, and is it bandwidth terminology? Yes, jitter is also a bandwidth terminology. I don't want to confuse people with jitter at this moment, because we are in CCNA and jitter is a bit high level topic. But if you have asked it, how do I explain it? Well, jitter is different than latency. Jitter is the measurement of change in the latency. So for example, if I am, let me do a ping again. So if I do ping, so what we want is that the latency should remain constant. So for example, if I have the latency of 72 millisecond, 73 millisecond, 55, 67, so I'm sending 4 packets, and every time the latency is different. So let's assume if the latency was 72 millisecond every time, it was fixed 72 millisecond, then we would say I have a jitter of 0. You understand? Jitter is the change in the latency. Is the latency changing? If it's not changing at all, we say jitter is 0. If our latency is changing, like in this case, sometimes it's 72 milliseconds, sometimes it's 55 milliseconds, sometimes it's 67. Now we say we have some jitter. We have variance in our latency. Sometimes it's low, sometimes it's high. We want in our network to have this latency as low as possible, meaning we want our latency to be as close as, we want our latency to remain same as much as possible. Because when it's closer to 72 millisecond, 55, sometimes 67, the application that we are using, specifically the voice and video application, they can actually adjust these small changes and process accordingly. But if your latency can jump and has a very high variance, meaning it has higher jitter, then the video and audio application cannot process it properly, and there are delays and problems. So jitter is mostly talked about with in quality of service and voice application, which we would talk about when we are talking about quality of service model. Okay. So why do we see copper cabling a lot in physical installations of networks? Well, it is because it is inexpensive. It is cheaper than all other options that we have. It is easy to install. Any technician can bring in copper cable and start making cables and start creating connectors. It's easy for them to do it. Compare that to fiber optic. It is very hard to do all of that. And it has low resistance to electrical current flow as well, meaning it is not easily affected. The signals traveling in copper is sorry, no, that's not what it means. It has low resistance to electric current flow, meaning that when you're using low power to send these signals, because it's not resisting that signal, so it can go a longer distance with a very small power input. But it has its limitations, problems. For example, it has a problem of attenuation, which is the longer the electrical signals have to travel, the weaker they get. So meaning that you cannot have a very long copper cable, generally speaking, more than 100 meters. All the copper cables in computer networks has to be lower than below 100 meters. Why? Because of attenuation. Because the longer the electrical signals have to travel, the weaker they get. So when you send a signal, it loses its power as it travels. So it cannot travel more than 100 meters. If you create a copper cable that is longer than 100 meters, your signal at the other end would be attenuated. It would be very weak for the receiving computer to receive it and reconstruct the message that you sent. It would be garbage, or it would have a lot of errors. The electrical signal is susceptible to interference. It has another problem in copper cable, is that there is electromagnetic interference if your networking copper cables are close by to the power grids or just normal power cables in which electrical power is going on. The electromagnetic interference can interfere with the electric signals that are going in your copper cable and corrupt the bits and information in it. So it has these two big flaws, yet we still use it. Okay. Because we do some mitigations. For example, we adhere strictly to the cable length limits, which is 100 meters. Just don't create a longer cable, then you're safe. Some kind of copper cable mitigate EMI and RFI, so electromagnetic interference and radio frequency interference can be reduced by using metallic shielding and grounding. So you shield these copper cables in a specific special type of shielding, which will help it to reduce the electromagnetic interference and radio interference from external devices. So we use that, and we can use there's another problem that is called crosstalk. We'll talk about it in next slides. That's a problem in these cables, but we can also reduce those by using twisted pairs. So let's see about that. So these are the different types of copper cable that we can use in networking. You must be more familiar with these ones, but this was also a copper cable, which is a coaxial cable. Some of those who have seen the TV cables, which uses coaxial cables for the TV networks, you might be familiar with this. They were also copper cables. They were also made of copper, but they were initially also used for computer networks as well, just like they were used for TV networks. But right now, the more popular one is the UTP, the unshielded twisted pair, and the shielded twisted pair. They're basically the same thing. With this one, only have extra shield that you can see a tinfoil shield here. That's the all difference. These are 4 pairs, 1, 2, 3, 4, and they are pairs. So they are, instead of 1, these are 2 cables. One is for positive signal, one is for the negative signal. So in total, you have 8 copper wires inside unshielded twisted pair or shielded twisted pair, okay, in which the signals transfer. So we talk about some of the characteristics. So the unshielded twisted pair is the most common networking media that we use in computer network. It is terminated with RJ45 connector. This is the standard for the copper cable for the Ethernet standards that we use today. That whenever you are using the UTP cables or shielded twisted cables, the connector type should be RJ45, which is the common networking connector standard that comes pre-installed in new computers as well, where you can plug in these RJ45 connectors. So it is a standard for this UTP cable. It interconnects hosts with intermediate network devices as well. So with this cable and this connector standard RJ45, you can connect computer to switches, switches to routers, routers back to computers, and so on. And this is how we build the networks. It has the outer jacket, which protects the copper wires from the physical damage. So that's just a covering. Then you have twisted pairs protect the signal from interferences. So you see each pair has this twist. This twist is basically to reduce the crosstalk. What is crosstalk? Well, these cable has signals going in, electrical signals, and they can induce magnetic interference in each other as well. So these twisted pairs that you see, there are in specific length that are given to them, which it depends on what type of frequency is being used to transmit traffic data in these wires, and that helps them cross each other's effects. And the color-coded plastic insulation, the color code is just a plastic insulation. So this is where you can see the actual cable is shown here. So this is, and the color coding is just to identify which pair you're working with. Shielded twisted pair is the same thing. It also RJ45 connector. You can use them interchangeably. The only difference is that it has extra shields here and here, which helps them from protect them from electromagnetic and radio frequency interferences. So in case if you are working in a data center or in somewhere where you have electrical cables or power grids or batteries that are very close by your networking cables, they can corrupt data traffic using electromagnetic interferences in these cables. So in that case, never use unshielded twisted pair. You can use unshielded twisted pair in normal circumstances where you already know that there are no interferences in your wherever you are running these cables. You don't have strong electric wiring going on there, then you can use them. But if you fear that there are other electrical equipment that is going close by through these cables, then use shielded twisted pair. That will give you better performance. That's the only difference. We had the coaxial cables as well, which were initially used in networks, but no longer used. So it has also an outer cable, and it had like a shielded woven copper braid metallic foil. So this was so there was another copper here. So one was the positive, one was the negative, and this is the conductor to separate these two cables from each other. It did not have the RJ45 connector. Instead, it had VNC, N-type, and F-type of connector. Again, if you have seen the TV cables connecting, that is the exact same standard which was used in computer networks, in early computer networks as well. but they're no longer used in computer networks. Okay, they are just here for you so that you know the historical significance of this. Now, again, we talked about these things. So in UTP, you can see here the twists. So for example, this is brown and brown-white pair, and you can see the twists are different in this one compared to this one. So this is more tightly twist than this one. And that is for a specific reason. That depends on what type of frequency in this pair is running. And to reduce the crosstalk or interference between themselves, these twists help in that. So it negates each other, and it depends on the frequency of the signal that is going on. And so that's why this is an important thing to note down, that the twists in these cables are not just random twists. They are at very specific length, and all these twists are different. So if you are working with the cable and you're creating a connector, you cannot just untwist it and twist it back by hand, thinking that it came back to the same place, because these twists are very specific. It comes from manufacturer. You don't untwist them and twist them back. Okay, so you only untwist them enough for you to create a connector, and that's all. So we talked about TIA and EIA. That is the organization which is looking for the standardization of these type of cables. So TIA, EIA 568 standardized elements like what cable types you would be using, what would be the maximum and minimum lengths, what type of connectors you should be using, how you would terminate these cables, and how you would test if your networking cable would work. So this is an organization that is defining all these things, and based on these definitions, these organizations are improving these standards almost every few years. So for example, IEEE electrical standards for copper cabling are established by IEEE. So the TIA EIA is looking for these physical standards, and IEEE is looking for the electrical standards, like what frequency of signal you can send in these cables, what would be the voltage level for those, and that's how they are modifying it. For example, every time they modify the frequency or the voltage level and the quality of these cables, they improve bandwidth. So, and then they give it different categories, like this is a UTP category 3 cable, which look like this. And then they added twists into it. So this was basically only supporting 10 MBs of speeds. To increase the speed on the same links, you had to modify a few things. For example, they added twists to these pairs, which reduces the crosstalk and interferences, and then added shields and so on and so on. And that was modified up to, and then we called it category 5 of UTP cable with this enhancement. And then it started giving you 100 MB of speeds. And then it modified it even further with 5E, and then it started giving you 1 gigabit of speed. And then the category 6, with further modification, more shielding, protecting it from all sort of errors and interferences, the category 6 cable could support 10 GBs and so on. That's how different categories supports different bandwidths with more improvements, with more characteristics added to it. And this is the job of these organizations. That's why we have these organizations, because they can keep improving it. Okay. This is the RJ45 connector, which most of you would be familiar. This is how we connect computer and switches and routers together usually. Why? That's what we are studying here, because it's copper, and this copper cable has this UTP as a standard, which is commonly used in network. Why? That's what we just talked about. Why are we using this? Because it's cheap, it's easy to work with. The termination of the connector is easy. You can just get a cable. You have a technician who can just train on it for 1 or 2 days, and he's able to start making these connections. However, length of the cable you need shouldn't be longer than the 100 meter, and they can just cut it and connect these connectors together and connect everything, and everything starts working. It's cheaper and easier to work. That's why. So You could also have the wall jackets that where RJ45 connectors, these sockets where RJ45 connectors can be plugged in. So if you are doing installations in the drywalls or something, then you would add these where the RJ45 connector can get connected. And this is how exactly where your computer where RJ45 connector can plug in, your network interface card in computer would have this socket as well. Otherwise, you cannot connect it. So wherever you see this socket in your computer or a server, that means that's where your network interface cards is. And that's what is defining which type of connector or cable could be connected to that computer. One of the common mistakes some technicians do is that when they terminate this connector, you see, look at this cable. This is a perfect cable, right? An example of perfect cable, the connector is sealed in. You don't see any cables coming out. This is what comes from manufacturer mostly. So you can just go to a computer shop and buy this. They call it patch cables as well, right? So you just buy it. It is pre-terminated. You just tell them, I need a 10-meter cable, I need a 100-meter cable, and so on. They have pre-made these from the manufacturer, and you don't have to. Don't know how long a cable you need, and there are needs. Then you just buy a cable, and a technician will it himself. The pen is maybe, but this area, this shape you see, it is not fully inserted here, and this is the place who presses it and closes on this jacket so that everything holds together. And this is moving, and maybe to computer working there. It can out problem. Whenever you're working, you have to make sure all the cables are area all is going all inside, so that if you try to pull out the cable, you won't be able to pull them out of the place. You have to physically look for these signs in the cable. If type of okay, so we talk about straight through and crossover UTP when we are talking packet trace. These and these are defined by EIA. Okay, they defined standards. One is called 568A, another is called T568B. All right, thank you. Okay, so we were talking about EIA, TIA, T56, T568A, and T568B standards. So the standard is for the color coding that we use when we are terminating the connector on UTP or shielded twisting pair. Okay. We are not taking a break today because this is a smaller module. We're just going to finish it within 15 and 20 minutes, and you're free to go. Okay, because this is a smaller module, we can just finish it off. So we are almost done with the UTP or copper cable. Then we have fiber optic and wireless, and then we are done with the physical layer. So we have two standards by EIA, TIA. These two standards basically says when you're terminating these cables, what order of the color coding pairs you should, in which order you should connect them. So these are the two orders. And you can say, starting from pin 1, and you have to see that you can start from green, white, green, and then orange, white, and then blue, blue, white, then orange, and brown, white, brown. This is one sequence. Then this is the one sequence you can use, or this is the second sequence you can use by standard, okay, when you're terminating. Now, if you see the difference, you don't need to memorize the color numbers. Yeah, we are getting to that, Abid. We are getting to that, okay? So if you look at the pairs, the pair 1 and pair 4 are same in both cases. The only difference is between pair 2 and pair 3. And they're flipped, if you see. You just have to change the position of pair 2 and pair 3. And there is a quicker and easier way to memorize this is to just remember this number, 1326. Okay? So if you remember this number, then you can easily see what the difference is. The number 1 is switched with number 3, so that's the 13. And the number 2 is switched with the 6, that's 26. So if you remember 1326, you know both standards. This is the difference. And you can see it here. So if you flip it with one with 3, it becomes, so what is number 3? It is orange white. So number 1 becomes orange white. And what was number 1 here? Green white. So number 3 becomes green white on this standard. Similarly, between 2 and 6, 2 is green. Now green becomes 6. And 6 was orange, 2 becomes orange. So you are just switching the positions of these two numbers, 1326. So if you remember 1326, you know the both standards. That's the only difference between them, okay? But why? The question is why? Well, the reason is that whenever you create a cable like this, right? Let's say this is the cable. And here you create a connector here, RJ45, and this is the connector. It has 8 pairs, like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 connectors, right? To quickly, we are going to talk about this later on again in other different modules, but just to give you a quick idea why do we have these two standards, is the reason is that if you have a computer here and a computer here that connects using this cable, inside computer you have this socket where it has 8 pins to which these RJ45 would get eventually connected to receive and transmit bits, right? In these bits, it is predefined which pins are transmitting and which pins are receiving. Again, I'm not going into details of which pins are transmitting and which pins are receiving. I'm just giving you a very quick and crude example that there has to be some definition that some pins are transmitting data and some pins are receiving data. We will talk about this in a lot more details later on, okay? So if let's assume that the pin 1 is transmitting and pin number 8 is receiving, and all the computers are created by manufacturer like that, right? Then this computer would also have pin number 1 transmitting and pin number 8 receiving, because they are the same computer. All computers are created exactly the same way, right? So now if you just connect this, so let me remove the cable, that would be easier. Let me just remove this cable. Okay, so if computers were created like this, and if I have 8 pairs of cable inside my copper UTP cable, right? If I connect the pin 1 to pin first cable, which is, let's say, green white, then it would get connected to pin 1 here. And the pin 8 would get connected to pin 8 like this using this key. I hope you're following me up to this point. If there's any confusion, just let me know. Are you following me, guys? Okay. So if you do this, thank you. If you do this, what is the problem here? The problem is that, let's say this is computer A and this is computer B. The computer A is saying that whenever I need to send something to computer B, I will choose this pin 1 and send a signal on it, and computer B must receive it. But the computer B is also saying that if I have to send something, I would also send it using bit 1, which is a problem. Yes, exactly, Peter. Because the computer B is saying that, hey, if you were to send me something, I'm ready to receive it on pin number 8. But you're not even sending it on pin number 8. You're sending it on pin number 1. Why is that? That's a problem. We cannot communicate in that case. So this is why we had to, when we are connecting two same devices, this is important, okay? Two same devices, which is a computer, because in this case, we picked two same devices. If two same devices want to connect, I have to make sure that the pin number 1 gets connected to pin number 8. Pin number 1 gets connected to pin number 8, so that when I'm sending something, it is received on pin number 8, not on pin number 1. Similarly, the other computer, when it sends something on pin number 1, it is received on pin number 8. So that's why you need to cross the cables inside the cable in UTP so that they are cross-connected. And the actual numbers that we need to connect are actually these ones. If I'm sending something on pin number 1, the other computer must receive it on pin number 3. If I'm sending something on pin number 2, the other computer must receive it on pin number 6. And that's why when we are creating this cable, one side of the RJ45 should follow this standard, and the other side of the cable should follow this standard. If we make sure that our cable is, both ends of the cable are following these separate standards, then we have automatically crossed those cables. And then we can connect these computers together and they will communicate. That kind of cable is called a crossover cable, in which one end is following the T568A and the other end is terminated with T568B. Where do we use the crossover cable? We use it whenever we are connecting two similar devices. For example, two computers, host to host, or two switches, switch to switch, or two routers, router to router. Whenever you have same devices that needs connectivity together, you have to use a crossover cable. Okay? Whenever you need two different devices connected, then you can use a straight through cable. What is a straight through cable? Whose both ends are either this or that. They just have to be similar, whichever standard you follow. Even if you don't follow any standard, it's still okay. They just have to be exactly the same on both ends. When do we need a straight through cable? Whenever a host to network device is connected. What does that mean? Well, in case of same devices, you need to cross the cables because they cannot the transmit pin cannot be connected to transmit pin. So similar devices like computers, all computers have exact same position of the transmit and receiver pin. But if you pick a router and a computer, because it's a layer 3 device, a computer is also considered a layer 3 device, but a switch is considered a layer 2 device. So we think of layer 2 device as a separate thing from layer 3 devices, right? So a computer and router is considered a similar device. So even if you want to connect a host to a router, that is still a similar device. You'd still need a crossover cable. But if you want to connect a host to a switch or a router to a switch, that is connecting a host to a network device. That's when you can use a straight through cable. We also have another kind of cable, which is called a rollover cable, which was Cisco proprietary, which had all the ports switched over. But most of this is now obsolete. This was for older devices when these things were really need to be that way. You had to Be very sure that you're using straight through cable or crossover cable, depending on what you are connecting. But look at this one. Considered legacy, specifically crossover, due to most NICs, all the modern network interface cards that we have today on all the modern routers, switches, and your computers, they have a specific feature called Auto MDIX, which can automatically detect which pin is transmitting and which pin is receiving, and it can adjust itself according to that. So you don't run into this problem at all in modern problems. Yes, the rollover is also a console cable. Yeah, rollover is a console cable. So when you buy a console cable, it's automatically a rollover cable. But again, these are not problems anymore. Okay, you can just take out a straight through cable whose both ends are exactly same, whichever standard is following, or even if it's not following any standard, just make sure they're using the same pattern on each end, and you can connect anything with that cable. This information is all just there for historical reasons so that you know how things were. But now we have Auto MDIX on network interface cards, which can auto sense these which pin is transmitting, which pin is receiving, and they can adjust their positions based on that, and you don't have to worry about all these things. Okay, so that was just a very quick introduction to the UTP. So we will be talking about these things more again later. Okay, this is just very beginner friendly topic at this point. Okay, a second option from other than the copper cable is the fiber optic. So fiber optic is not as common as UTP because of the expenses involved. Fiber optic is expensive. The cable is expensive, handling is expensive, the technicians are expensive, the tools that you need to terminate these cables are expensive. Everything related to fiber optic is very expensive. So that's why you don't see it more commonly in the enterprises. They're only used by ISPs for long-haul communication and connecting cities together. They're ideal for some scenarios, so it transmits data over longer distances. So whenever you need a longer distance communication more than 100 meter, because the copper limitation is 100 meter, and you also need a higher bandwidth than the copper, then you would use fiber optic. Okay. The benefits are that it is less susceptible to attenuation, meaning you can create a very long fiber optic cable more than 100 meter. You can create 500 meter and 1 kilometer, and there are some testing being done for 100 kilometer fiber optics as well. So that's the reason is that the attenuation problem is less, meaning once you send a pulse of light in fiber optic, that pulse of light can go very long way without losing much of its power. It is also completely immune to electromagnetic and radio frequency interferences. So because those are electromagnetic waves, they cannot affect light. So that's also a good thing. They cannot affect light in a sense that we are using pulse of lights. We are not using frequency or modulation techniques. They are made of flexible, extremely thin strands of very pure glass. Sometimes it's also made of plastic as well, so it's not always glass, but the good quality ones are always made of glass. It uses either a laser or an LED to encode bits as pulse of lights. So in order to send the bits in these fiber optics, in your network interface card, you must have a laser or an LED, depending on the quality of your network interface card and type of network interface card. You would have to use that laser and LED inside NIC, which will convert or encode the bits into pulse of lights. So the speed of or the bandwidth of your network or the NIC or the fiber optic depends on how quickly this laser or LED can send those pulses within 1 second. That would define its bandwidth. So it has to be very fast to send 1 gigabit of information in 1 second. That means it's like 10 power 9 times in 1 second. It is switching on and off like millions of times, millions of times. So the fiber optic cable acts as a waveguide to transmit the light between the two ends with minimal signal loss. The fiber optic cable, it is just a guide, a pathway for the light pulse to travel inside it. Okay. This is how it looks from the inside. I mean, this is just shape. The actual size of the fiber optic inside the glass part of it, it is thinner than the hair. So you hardly can see it, but everything that you see in your hand and when you're handling it, that's all just a cover for it for protection purpose, because the actual glass inside it, it's very thin, it's very delicate. So there are two types of it majorly. One is called single mode fiber, another is called multi-mode fiber. Single mode fiber has a very small core, like 9 microns, thinner than the hair. And because it is so small, the light travels in a straight line usually in it. And because it travels in a straight line inside it, that's why the single mode fiber can travel inside the single mode fiber. The light can travel very, very long distance because it has a smaller core, and it uses very expensive lasers in network interface cards as well, and that's why it can support a very long distance. So it's, whenever you see a single mode fiber, that means you are connecting two cities together. So it could be in kilometers, like 20-kilometer cable. You need 20-kilometer cable, you need single mode fiber. But it is going to be expensive, obviously. Everything related to the single mode fiber would be expensive. For multi-mode fiber, we have bigger microns, so it's not as thin and small like the single mode fiber. And that's why the light travels not in a straight line, it keeps bouncing off. And because it keeps bouncing off of this glass or plastic material, it cannot go too far. So it has a larger core, it is less expensive, and it uses LEDs in network interface card instead of lasers, because lasers are expensive. LEDs can transmit at different angles, and it can support 10 gigabits over 550 meters. So the problem is that it can give you a good bandwidth, but you cannot have it connect for longer than the 550 meters, like a half kilometer. But it's still better than the copper, because it can go longer distance than the copper, which is limited to 100 meters. So where do we use fiber optic cabling? We use it in enterprise networks in some cases, not everywhere, for the backbone connectivity. For example, if you have a university campus and it has multiple buildings in close vicinities, so to connect two different buildings, you would probably use a fiber, but inside the building, you would be using copper cabling. So that's why it says in enterprise, for the backbone, you would be using fiber whenever you need to connect two devices that are further apart more than 100 meters. That's when you would be using fiber in most cases in enterprise. Other than that, fiber is used by ISP to provide connectivity to your home, to give you internet connection using the fiber to the home technology, or for the long haul networks when they are connecting to different cities in the country, or when different continents and countries needs to be connected using submarine cable networks, which are cables under the sea, which are all fiber optics. Okay. But again, fiber optic is very delicate, small, thin, and can be easily destroyed. So the undersea cables that you see, they are huge, big, and heavy. That's not because the fiber optic is heavy and big. The fiber optic is still very small and thin, and thinner than the your hair. But the big bulky things that you see on submarine cables, if you search them or you have seen in any video, that's all just for protection. So that because undersea they are exposed to harsher condition, salty water, and sharks and so on, and there are ships going on and they have anchors. They could be damaged by many things. So that's why all the bulky things, the black materials you see around the fiber optic, that's all just protection. Okay. Fiber optic has multiple types of connectors depending on the which type of fiber optic you're using. It uses straight tip connectors, lucent connector, LC, subscriber connector, SC, or duplex multiport connector. So these are different types of connector that you can see in fiber optic. The quick identification between different fiber optic is the color coding. So whenever you see orange color, that means it's a multi-mode. Whenever you see a yellow color, that means it's a single mode. So SM and MM. Orange color, it is multi-mode. Yellow color, it is a single mode. What is the difference? Single mode is expensive, goes longer distance. Multi-mode is cheaper. It has a limit of 550 meters. distance. Okay. Here are some comparison between fiber and copper. So bandwidth supported, usually UTP or copper cabling has lower bandwidth support in compared to fiber optic. So fiber can support up to hundreds. These days, even UTP can support up to 100 with category 6E cables, but they are as expensive as well, like fiber optic. But still, even if that's not a big difference, the copper cable has a problem that it cannot be run more than 100 meters, while the fiber optic cable can be ran up to hundreds of kilometers. The UTP cable has immunity to EMI? No, it has very low immunity, meaning it can be affected because of electromagnetic and radio frequencies. It can interfere with it. While in case of fiber optic, it cannot be affected. It is also not good in electrical hazards. The electrical power lines will cause problems with the UTP cabling interference. It cannot do that in fiber optic. So fiber optic is better than UTP in most cases, but the problem is the cost. The media and the connector that we use with UTP cabling, the RJ45 and the copper cable, it is cheaper. It costs low. Installation doesn't require a lot of skills. Anyone can do it. We can do it, and technicians can do it. And it doesn't need a lot of safety precaution. But the problem with fiber is that its connectors are expensive. The cable itself is expensive. Its technicians are expensive. We cannot install them. We need a specific technician with specific machineries to terminate these cables and fix things if they are broken and so on. And it also needs a very high precaution from safety perspective, because these cables, if they're broken, they have a very specific kind of glass and chemical materials that could be cancerous if it goes inside human body somehow, if you cut yourself with it and so on. So that's a quick comparison between copper and fiber, and that's why you see that these are the cost are the reason why we use UTP or STP copper cabling inside enterprises, and the distance and speed is the reason why we use fiber optic for the long haul communication connecting different cities, continents, or undersea cables. So these are the characteristics of these different media which decide where we would use what kind of cabling. Okay. Finally, the wireless media. Of course, as you all are familiar with wireless media, it doesn't use physical cables. It uses electromagnetic waves. So that's why it's called wireless. There are no wireless involved. But it has a coverage area, so it has some limitations. Its coverage area is effective coverage area can be significantly impacted by the physical characteristics of the deployment location. So depending on where you are deploying your wireless access points to cover a specific area where you could be connected or your devices could be connected, it depends on the physical location. So if there are a lot of steel doors and heavy cement used, concrete used, then it will affect the coverage area. So if you deploy a wireless access point in open area, it could support like 100 meter and 150 meter distance from where devices can connect to it. But if you deploy a wireless access point inside a closed house with the concrete in the wall and steel doors and so on, and everything is closed, that will affect the coverage area. So then the coverage area of devices that can connect to that access point could drop down to up to 50 meters. Okay. It is highly susceptible to interference. If there are other wireless devices or other devices that are running on the same frequency that your access point is running, it will heavily interfere with it, and it will affect your network. Security is also a problem because you are broadcasting your information and anyone can try and read your signals. So that gives you a security issues as well. And it's also a shared medium because everyone, so if you have 10 users connected to your wireless access point and your wireless access point total capacity of bandwidth is, let's say, 54 MB, that was the common one that we've used in a lot of home networks. then all the users are sharing that bandwidth on the wireless access point. So if everyone is using, for example, if there are two users connected to your wireless access point, they would have to divide the 54 Mbps bandwidth between them. So each one is only getting 27 Mbs. If you have 10 users, then everyone is almost just getting a 2.5 and 2.5 or 3 Mbs. So the more users you connect to an access point, the slower the performance gets because it's a shared medium. The bandwidth keeps sharing and dividing between those people. So there are a lot of disadvantages of wireless, but because it has one advantage, which is that it is very easy to install and get connected devices without wires, that's why we keep using it, okay? So there are different wireless standards that were created for depending on what characteristics you want in the wireless network that you are creating. For example, Wi-Fi is just one standard, which is the marketing name for this technology. The actual technology is IEEE 802.11. This is how technically it is identified, this standard. This standard defines that, I don't know, maybe it's 100 meter or up to 200 meter, that any device that is following the Wi-Fi standard, its signals cannot be stronger than 100 meter or 200 meters. So only so you spread out only 100 or 200 meter signal because it is using a shared frequency, same frequency everywhere. Everyone is using this free frequency. If it was allowed to create access points that can work up to, let's say, 500 meter or 1 kilometer, which is totally possible, but standards and vendors and these organizations like IEEE, they don't allow vendors to create such access point. The reason is that you would be interfering with each other. So if I put access point which can throw a signal up to 1 kilometer, and you also have the same device in your home and everyone has it, then everyone in 1 kilometer would be interfering with each other and nobody would be able to use this standard at all because there will be a lot of interference. That's why they limit the power of the access point up to 100 and 200 meters so that they cannot throw a signal longer than the 100 or 200 meters, so that you can, everybody, and that's why everyone can use it in their home. Everyone is using the same frequency and still not interfering because of this coverage limit that is put on the Wi-Fi. Then you also have Bluetooth, which is also a type of a wireless connectivity that is standardized for two computers or two devices, smaller devices, to work in an even smaller range, like maybe 10 or 20 meters, and the Bluetooth doesn't throw a signal longer than that because it is purpose is to just quickly share or connect something in a very close vicinity where you are physically available. Similarly, we have a WiMAX for a long distance wireless communication using point-to-multiple topology to provide broadband, like wireless internet connectivity to entire city. That's the standard for that, and so on. So there are different standards for different situations and applications defined by IEEE, and you can pick whichever one of wireless connectivity you want to use and create a network with that. But you are just most familiar with this one, and this is what we are going to talk a lot about in our CCNA course, okay? So for creating a wireless local area network or a wireless network, you need two things. You need a wireless access point, which everyone has it at home. The ISP installs it. What is a wireless access point? It concentrates a wireless signal from users and connect to the existing copper-based network infrastructure. So if you have a switch, you can connect through a cable a wireless access point, and now this physical cable, when wireless access point connects to it, now it gives you an ability that all the wireless devices like your phone and tablets and computers, if they have a wireless network interface card, they can connect to this access point using wirelessly, and then this traffic would be transferred back to the wired network, and that's how you actually connected to the wired network using wireless. So this access point is actually extended this wired connection and converting it into a wireless network. That is the purpose of wireless access point, basically. But in order to connect with these wireless access points, your device must have a wireless network interface card. And if your computer doesn't have it, your laptops and mobile phones always are, they do have this wireless network interface card. It has an antenna. A wireless network interface card is basically, it has an antenna, but you don't see these antennas in a laptop and your smartphones because they are installed inside the packaging. You don't see it on the outside. But if you have a computer or a laptop which doesn't have the wireless NIC, you can just buy a USB wireless NIC and plug into the USB, and that's basically your wireless network interface card, and then you can connect to the access point using wireless. Okay, so two things needed: only wireless access point, which can extend the physical network and convert it into a wireless network, and then you need a wireless network interface card in the devices so they can connect to that access point. There are a lot of different standards for wireless access LAN, which we will be talking in a separate module. There is a separate module specifically for wireless, which we will be looking at. Okay, so we have a packet tracer where we can see these things that we talked about, physical things in physical topology. What I'm going to do is, because we haven't taken a break and we want to finish this off, what I can do is that I will throw you a recording of these labs, and you will see when you explore it in the recordings, and you can see, watch it, follow it, because there's not a lot to do configuration. We just want to see inside the packet tracer these different types of cables and how you can pick and choose between these different types of cables in different situations inside packet tracer, just so that we reinforce the learning that you have done through the theory that we covered today. Okay, so go to your Netacad account, module 4, do the practice questions over there, and download the packet tracer, go through it, and I'll give you the recording and the solution for those packet tracer as well. And let's compare it and come back tomorrow and we can talk about it if you have any issues. Okay, yes, I will be sending you the recording today. All right, okay, so we will wrap it up here for today, if it's good with all of you. Otherwise, I can stay and talk more. All right, so I will be giving you recordings, so make sure you do these quizzes in your Netacad as well. Okay, don't just come here for the classes and watch the recordings. If you are not going inside your Netacad account and you're not doing these quizzes at the end of these topics and end of the modules, you will not be reinforcing what you're learning in. So you might feel right now that you came to a class and you learned a lot of things, but trust me, you will forget about them in 2 days if you don't do these quizzes. So the quizzes and the labs are there so that you can reinforce what you learned here, and that's how you retain this knowledge. Okay, yes, Muddin, you have a question. What is the question? Aubrey saying about PoE. We're not talking about PoE a lot. Maybe in some next module, other modules, there would be some discussion about PoE, but at CCNA level, there's nothing much about PoE that we talk about. Unmute me. Okay, let me see, because I muted because you can unmute yourself. Yeah, you can unmute yourself now.
Okay, I couldn't before, but now I can. I wanted to ask, actually, I'm in module 3, so I'm in module 3, quite all right. But I remember you once said the checkpoint is more important in as much as you are checking the checkpoints, even if you don't have 100% complete of each module. But if one part is checkpoint, one is on the good side, right?
Yes.
Okay.
Yeah, that's how it is. So the progress bar that you see in the Netacad for how much you have covered, that's just for you, so that you know that how much you have studied and went through the content, and there are videos and there are small quizzes here and there with 4 and 5 small questions. That's just all for you, for your learning. For the badge requirements and everything and scoring, that's where the checkpoint exams are. Okay. Okay, Nicholas says where I can WebEx I can find the videos. If you are in the WebEx group that is called Live 2026 February CCNA class, if you're part of that class, Nicholas, you will see the postings very soon. So in about an hour or so when the video is processed. Every time I post a new video, I post the previous videos as well, just so that you can quickly access them. So Nicholas, if you are in the group, you will get them, okay? I don't know why, Abid, why are you sending me your email here? I don't know.